In the previous video, we showed how to generate absolute ligand binding systems for free energy calculation. This video continues by showing relative ligand binding using amber with the amber force fields. The protein we will use is 4DJW, a beta secretase 1, or base 1 for short, complex with an aromatic ligand named 0KP. We will also show how free energy calculator handles ligands with differing charges. Start by going to Input Generator and finding Relative Ligand Binder in the Free Energy Calculator submenu. Since the crystal structure contains only a soluble domain, leave the system type as solution. Enter 4DJW in the text box and click Next. On the Model Selection page, we see two copies of 0KP. Since the Free Energy Calculator modules only handle one binding site per project, we choose the first 0KP molecule and deselect the other small molecules and the second 0KP copy and its associated protein chain. On the PDB Manipulation page, we will leave all options at their defaults and click Next. Again, make sure to save your job ID. When PDB Manipulation finishes, make sure to view your structure. On the Solvent Options page, we can also leave the settings at their defaults. We can view the generated CHARMM topology for 0KP by clicking the link to its RTF file. Notice that the charge of this residue is 0, and this will become important later. Now, close the topology window and click Next to generate a solvent. When CHARMM-GUI finishes solvent generation, we can simply click Next to set periodic boundary conditions and perform a brief energy minimization. Since we removed all other ligands, there is only one option in the ligand drop-down menu, so we can simply click Next to go to Relative Ligand Binders upload page. On this page, we could draw combinatorial structures as we did in the previous video. However, this can become unwieldy if you have a large number of ligands to test. So in this case, we will upload an SDF file containing 36 ligands. You can obtain this file by clicking the link in the video description. We will also use the Closed Minimal Perturbation Path option. When your ligands are selected, click Next to set the ligand pair options. On this page, notice that there is a single ligand, number 1, which is not included in the path. We can also see this in the similarity score matrix, as all pairs involving ligand 1 have a note telling us that the pairs do not have matching charge. If we click on one of these pairs, we can see that this nitrogen atom in ligand 1 has 3 bonds, giving it a neutral charge, whereas the corresponding atom in ligand 2 has 4 bonds, giving it a positive charge. Thus, we can see that the free energy calculator modules will not include a molecule in the perturbation path if its charge does not match the others in the path. In the input generation options, notice that if we choose the amber force field for amber TI, we get more options, including an amber force field checker. Note that because we have a large number of ligands, it will take a few minutes to verify ligand force field generation. If we want to use a different force field model for a given component type, this is where we would do so. Note that amber TI is only compatible with the amber force field. We can also choose the unified or split protocols, or both, and we can change the number of simulation replicas. Then we can proceed to the next page. Again, because there is a large number of ligands, it will take several minutes to generate inputs. In this case, it will take 5 hours to generate all the system and input files. For more information about conversion time, please see the table in the video description. As you download your project archive, make sure to read the simulation instructions on the final page. In the downloaded project directory, we have an amber directory for our amber simulation inputs. Inside that directory, there is a README file demonstrating how to run amber TI simulation.